All right. Hello, welcome to lecture 7. Today I'm going to be talking to you about the use of a new structural material, which is timber or wood. So my question is, can you build structures from wood? Yes, obviously yes. I have a photo here of a building under construction entirely from wood. As a matter of fact, wood is probably much older construction material than steel and concrete. These are relatively modern, more advanced, stronger materials. But since the beginning of time, pretty much, mankind was using trees. Trees are readily available in some areas of the world. So it depends on where you want to practice engineering, where your local market is mainly made out of. It will dictate the price and availability of timber and wood products, even if you don't have forests. So where do you get wood? Where do you get trees? Forests. Usually it's like forests that are sustainably kind of renewable, that you can farm them. You can farm the wood sustainably to keep a constant or a steady supply of timber. And if it's not too far from your project, you can actually farm the tree and do some processing on it, cut it into standard sizing, and then you ship it on site. You can create different products with wood. You can create sheets. You can create planks and logs and different types of individual elements, and you can definitely use it in construction. It's lighter than steel, so individuals can actually carry these studs. These vertical elements, they're called studs, and then you put sheets on it and you can form walls. Then you can paint it, finish it, and this is very typical for like single family residential buildings, things like that. It's relatively fast, it's affordable if the wood is available, and it depends on which part of the world you're practicing engineering. So if you're going to design a structure made out of wood, how strong is wood? Are all trees the same? Are they all the same size?
No.
Okay, so how do you specify the strength of wood?
Reading the laboratory tests.
Yes, it depends on the species of wood. What kind of tree is it? There are mainly two different types of trees. Or different type of wood and timber. Also, it depends on how healthy the tree is. Some trees have problems, have like flaws or faults inside of it. It makes the section weaker. Some finishes of wood take some chemicals to preserve or treat the wood. This could affect its capacity. So there are few factors that will eventually help us as structural engineers determine what is the strength or the capacity or the maximum stress that wood can take. There is also another important aspect, which is what is the load direction on the fibers of wood. If you're loading the wood section parallel to grain, its capacity is different if you rotate it 90 degrees and apply load perpendicular to the grain of wood. So the direction of load matters. The species of wood matters. Also, the grading of wood. So when you say some trees are healthier than others, so when you cut them into boards and into small pieces like that, you can have visual grading. You can have visual inspection. You can look at the cross section of the wood segment and you can grade it visually. This is like structural kind of grade number 1, structural grade or number 1, number 2. It depends on how many kind of problems or deformities that you anticipate in the wood grade. So usually this is all done for you, and you as a structural engineer will specify, in order to build this house or to build this structure, I need structural grade, I need this species of wood, and you're gonna assume accordingly the strength of wood. How tall, how far can you build a wood in a structure entirely from wood? 2 stories. That's about it. Like the tallest I personally designed was 3. I think you can go maybe 4 or 5. It depends on the spans, obviously. Above, more than that, you need a different structural material. So what other construction materials that you can use other than wood? Reinforced concrete, steel. You can use masonry as well. Masonry is like when you build with bricks, with blocks. What if you want to build a very tall building, like a super high-rise building? Use steel and concrete. There you go. So if you're building something, wood is available. It's usually not very big size. You might as well use wood as a construction material. These are the 2 types of wood. You can use 2 main categories to describe the wood products, either softwood or hardwood. Softwood is mostly for construction. Hardwood is much stronger, but if you drive a nail through it, it will split easily. So it's harder to work with and does not take connections easily. It's very expensive. These types of wood are like, you can call it the fancy wood. You can create like furniture from it, or like floor finishes. Things like, you know, ash or walnut, cherry, wood, maple. These are like Canadian products. They're beautiful. If they're stained, you can have like very beautiful finishes and floors from it. They're expensive, not very common for construction. Softwood is much more used in construction, and the reason why is it has to do with the species of the tree. Softwood trees usually are evergreen. They don't lose their leaves every year, so they grow fast. When they grow fast, they kind of accumulate mass quickly, so the density is not as big as hardwood, which these types of trees, they shed their leaves in the winter, so it takes them more time to grow. So when they grow eventually, they're denser and they're heavier. So this is the main categorization. Now, when you look at a typical cross-section of a tree, how do you transform this into smaller pieces that you can work with? You actually use a saw and you cut it. That's the most basic type of wood. It's called sawn lumber or sawn timber. You put the log through the saw and you get these pieces out of it. You can get different pieces, and I need you to observe the grain of the tree. If you look at this board or this piece, when you load it parallel to grain, it has a different capacity. If you load it perpendicular to the grain, to the fibers of wood. This is something the code specifies. You can assume the strength of wood parallel to grain that much, perpendicular to grain that much. So when you're applying it on site, you kind of need to figure out, is this wall going to be parallel to grain? Is the baseboard going to be like perpendicular to grain? You think about it this way. All right, so now we understand there is softwood and hardwood. After this process, usually there are like some unused parts. You can't just like use 100% of the trunk. So you can create out of it something called engineered wood. So engineered wood is a cross section or a composite of wood that is made out of smaller pieces. So there are a few ones that I want you to be aware of. The first one is called Glulam, or glued laminated timber. What it is that you get layers of wood, and then you glue them together, and you can create a bigger section. Like what if you want to create a beam that is very deep? It's not very easy to go and find a tree that is that big, but you can create it from like smaller pieces and glue it together to create bigger beams. Obviously, if you're going to use it as a structural element, now you need to take into account that this section did not naturally grow on a tree, it was actually glued. So the glue between the layers will change its behavior a little bit. Okay, another one is called the LVL, or Laminated Veneer Lumber. Laminated Veneer Lumber. You can create beams out of it, you can create different products out of it. It's like thin layers, and you can create like a beam, or like you can create like a bigger size, and you glue it together. The Glulam would look something like this beam. You know this arched beam? You can create curves, it's much deeper. Plywood, you can create sheets to cover up walls, or even floors or roofs, with, again, layers of wood. From the side product of sawing and the chips and the small pieces, you can actually compress them together into sheets. They're called like OSB, or oriented strand board. Same thing with like the fiber board. These come from products of the side product of like milling and sawing wood to create other engineered products of wood. I want to point you out to this product over here. This is called like an I-joist. The top and bottom flanges are big. It's like an I-beam. This section is very effective because it has materials at the top and the bottom of the section. This is where most of the tension and compression and bending is. And the web is just like to resist the shear. So it's made out of an engineered, maybe like an LVL, or some sort of like an engineered wood for the web. And the top and bottom could be like from a different wood material, and then you glue them together or you connect them together to create joists. So that would be an example for engineered wood. I have a diagram here that shows you the process pretty quickly. So you start with logs. Logs is like the tree, you harvest the tree, and then you cut it into reasonable lengths. You don't want to cut it too short because you want long boards out of it. So as far as you can, transportation, you can safely transport it, cut it, and then it goes into two directions. You either get sawn timber using a saw, you kind of cut it into standard sizes. You start maybe with like an inch by 4 inches, an inch by 6 inches, things like that. And the other path is peeled. So you create thin sheets of wood. And then you can create different products using these two methods. So just sawn timber, you can use it to create floors, you can use it to create columns. You can glue them together, just like that. You create glulam. The waste of cuts, the chip wood, you can create like the OSB, the orientated strand boards. From the sheets, you can create plywood, sheets of plywood, and create them together. And then you have all these products to build a building. I'll show you what a typical frame look like, but it will be like the joists. You put some plywood on it, and then finishes, and you create the wall the same way. You create studs from sawn timber, 14 inches on center. So you put them 14 inches on center. You put like a top and bottom boards, and then you build the next floor on top of it. I have a detail that shows you how to do that. So how do you connect wood pieces together? Any idea how to connect two wood pieces together? What's the first method that would come to your mind?
Maybe nails, or to have hollow parts and then figure them to be connected together.
Yeah, that's exactly it. Nails. When it comes to wood, first thing that comes to mind is like you nail wood together. So obviously, you can use nails to connect wood together. You can use something called like lag screws that actually will not just like punch through the wood, it will help into retaining the bond or the connection, especially if there is like reversible loading. Some connections actually result in squeaking. You know, if you walk on a wood floor, you might hear squeaking. Maybe you need like a screw rather than just a nail. And there are more robust connections. You can actually have bolts. You can have bolts to connect wood. You can have steel plates sunk in the wood piece and use bolts with it. You can have a detail, this is called countersunk bolt. So the bolt is sunk in the face of the wood piece, so it's not sticking out. There is actually no limit of like how fancy the finish or the look you want to get. You can create very beautiful buildings. Or if you want it just for practical reasons, if this is all going to be covered up, you can use steel accessories or ties to connect wood pieces together. For example, this saddle, it's called like a saddle. The beam is sitting on the saddle and it has these two sides over here to be connected to the column. So that's an interesting way to have a beam column connection. You can see how the beam is made out of layers. So this is sawn timber on layers. I can count like maybe 5 or 6 different layers. You can use them together as a beam. Same thing with the column. Do you see how the column is like 2 by 6 or like 2 by 4s? You put them side by side, and you obviously have to connect the 2 layers of the column together with nails, and the code will tell you some specification of minimum spacing, how many nails you need, depending on the force and the capacity that you want to get out of the column. I want to point you out to this detail over here. This accessory, I know this is used a lot. This is called like a hurricane tie. That's the actual name of the product of the manufacturer. This element here is part of the roof system. Typically, if you are in a cold environment, you might get snow loads. Snow loads are less if you slant the roof. So you can actually shed the snow load and don't let it accumulate on the roof. So if you want to tie the roof to the wall, you need these very thin steel ties to connect the roof to the walls or the rest of the building in case of a storm. That's actually, believe it or not, the effect of wind on the floor, on the roofs, is not actually compression, it's suction. When you do the wind tunnel analysis and you test the effect of a storm on a roof, the very high wind velocities will cause upward force on the roofs. There are a lot of videos on YouTube, you can look them up, in a storm where like a tornado or a twister or something like that actually sucks up the roof of a house clean off the building. So these ties will work as the connection between the roof and the ties. This is obviously things to think through when you're designing different types of structures with different construction materials. Because if you are designing a building from concrete, are you worried about the self-weight of the concrete floor being actually sucked out of the building because of a storm? The self-weight is super high. But when you get to wood, wood actually is relatively light compared to its strength. That's why it's an attractive as a construction material. I want to show you some structural elements that you can form with wood. So you can have a beam supporting a joist or a beam supporting another beam using what's called a hanger. Do you see that steel part with the black holes? The black holes where you can drive nails, and it creates like a nice place where like the joist can sit. and it will be hung, that's why it's called a hanger, it's hung off the perpendicular beam. This is a examples of a connection between a beam and a column. You can have it by bearing. The beam could just like be sitting on the column, or if there's some moment, you can introduce nails, dowels, or bolts. And obviously, when you get to the bottom of the structure, you need to find some foundations. So, based on what I said so far, what do you think the relationship between wood and underground structure elements? Is it a good idea? Why is that?
By water and
Water.
Moisture,
It's light, it won't hold weight.
it will deteriorate. If you bury wood unprotected in the soil with like the seasons, with moisture, with the elements, it will pretty much, in a very short duration, you will have no foundations to talk, to be considered. So what do you want to use instead? What would be a good material for foundations?
Concrete.
Probably concrete is very durable. You can use concrete. So same thing, you can have a connection between concrete and wood. You can use these accessories. Some of them are called a like wet cast, like you put this when the concrete is wet. So before the concrete hardens, you can plant or install this part in its location where you want it before the concrete hardens, so it's nice and ready to receive the column. Some of them are like more robust with like thicker plate to obviously take bigger load, and some can actually be installed afterwards. So you can wait for the surface of the concrete to harden, or if you want to add a connection after the fact, you can go ahead and drill holes in the concrete, install anchor bolts, and then connect to it these steel plates that have the capacity to accommodate a wood column. These are some of the floor systems. So how do you create a floor out of wood? You can create it from like the I-Joists. I talked about those. They're engineered product. You can put them on center with spacing on center. And the plywood, the sheathing, the boards on top, they don't have to span that far, right? So if someone is standing in between two joists, where is the weight of that person gonna go?
To joints.
To the joists. And what is going to transfer that load? The plywood. So this plywood, do you see the thickness of the plywood? So usually it's not very thick, and that's why it's not gonna span far. So you look at a floor systems like this, you can use it from Glulam, you can use it from Sawn timber, the standard sections. You can build walls just in the exact same way. You put these are called like studs. The vertical elements are called like studs, and you put them every so often. 14 inches on center is very common. And then you put plywood on top of it, and then you have a wall. Same thing with columns. I mentioned using more than one layer of Sawn or Glulam, and you can get different dimensions of columns. Typically, this is how a floor plan would look like. This is a plan view. This is an opening for like a staircase. So these are the joists, and do you see how they are running every so often? So when you put the plywood on it, the plywood is not spanning too much. You also want to cover up these joists with some sort of like boarding, and there are interesting connections that you can have between these boards, like a tongue and groove. It could be a single or double to connect this boarding, this decking, to create the floor, so that you can put finishes and put things like that. It's a different way of building. If you're not used to living in a house made out of wood, the sound isolation is not the best. You need to pay attention to moisture. It's not going to be very water friendly if you have like a bathroom with like leaking faucets and leaking taps. This all has to be taken into account when you're building with wood. So now this is the main idea that I wanted to share with you. What is wood? How do you get it from? How do you build with it? Now there is Eurocode 5 that has specifications. This is going to be our go-to reference for the design of wood structures. All right, so today's lecture was mainly the introduction, and I want to very briefly get into the bending design. So now that you've been through the steel design, can you predict what is the design process for like any other material for that matter? What are we expecting Eurocode 5 to tell us about wood?
Give it the next bending with shear.
Bending,
Plastic.
shear. Okay, that's interesting. We'll talk about this in a second. Yes, you need definitely the section modulus, but is it going to be plastic section modulus or elastic section modulus?
Elastic.
Why is that?
عشان التمبر بيكون لا من شتاء أو مية.
Because wood does not yield. A plastic phenomenon, this is only for steel. Steel is a very interesting material because it has this property. It doesn't fail suddenly. It will retain its strength over large deformation. That's what a plastic hinge is. So there are very few other materials that have this quality. So wood, the stress-strain relationship is mostly linear. It will take load, then it breaks suddenly. Same thing with concrete. Concrete will take compression all the way to like crushing, and then you'll have a violent, sudden, compressive failure. But you guys were on the right track. Go ahead.
I have a question. For timber or wood in general, why do they use it when it has so many disadvantages?
Because if it's ready and affordable and fast to build with, it's approved as a construction material. So if it's going to do the job and you can safely build with it, the code will regulate ways to deal with the disadvantage of wood, so you can use it as a construction material. Does that make sense?
Yeah, it makes sense. It's just because I know, like for example, we said we can't use it for foundation because of water and it's going to be
Yes. Yes, it's not very good for foundation.
Rain, snow,
Yeah.
Winter, summer temperatures, termites, insects.
Yes, but biological threats could actually deteriorate wood, and that's why it needs to be preserved, and sometimes the chemical, the treatment for wood will reduce its capacity. So there are few things that goes into determining the strength of wood, and this is exactly what I want to share with you over the next few minutes before we finish this lecture. So I'm interested to hear your thoughts to the end. So you said you're expecting Eurocode 5 to give us guidance on how to calculate bending capacity, shear capacity. What else? What do you need from the code?
On the section modules.
The section properties.
The elastic section properties, thank you very much. Deflection, what's the allowable deflection?
Yeah.
Yes, definitely.
Yeah,
It also gives us guidance, what's that?
It's strength.
Yes, it will give us guidance of how to calculate the strength of the wood section. It goes also into things like vibration, durability, how to take.
Limits of what, so to see if it satisfies or not limits.
That's exactly it. All right, so this is the equation for bending. In order to have a section strong enough to resist the loads on it, it could be exposed to bending about the strong axis and the weak axis. Most of the time, you have bending about one axis only. So if that was the case, you just you look into the formulas, you'll find the top part, this is the stress due to the applied moment, either about the y-axis or about the z-axis. The bottom factors, Fm, this is the design strength of wood. To find this, I would say this is equivalent to F yield with like the proper reduction factors. So there are few reduction factors that goes into calculating this term. So this term only has like 3 modification factors or 3 factors that goes into calculating it. Once you have it, it becomes like a simple stress analysis equation. The stress on the section should be less than the maximum stress that the section can handle, or the strength of the section. What about this Km factor? This Km factor takes into account if the moment on the section is on 2 directions, if it's about the strong and the weak axis. Sometimes it could be 1, you need to take full moment in both directions. Sometimes it could be less than 1, depending on the shape and size of the section. So for example, for a rectangular section, use 0.7. For other cross sections, you can use it as 1. And this is applicable for solid timber. You guys know what solid timber is? This is the sawn, the solid pieces. Glulam, the laminated parts glued together, or LVL, which is an engineered wood type that we talked about. All right, so let me walk you through what actually goes into calculating the maximum stress that wood can take. How do you get the maximum stress that wood can take? First, I need to know what species of wood, what is the grade of wood, and then the code will help us use some guidelines and assumptions to the modulus of elasticity for this grade. The maximum stress parallel to grain, maximum stress perpendicular to grain. And I have this table, I will share it with you. So this is how we're going to get Fm. But we need to take 3 other things into account and a material factor of safety. Are you guys familiar with like the gamma M? Do you know what gamma M is?
According to the code 1.
Yes. What's the well, that's for steel. So now we're dealing with wood. We're going to have different values for different things. So what is the function of gamma M? It's a material reduction factor of safety. So don't just like use 100% of what you think steel can take. You need to take some factor of safety into account. So which factor of safety you think should be bigger? Factor of safety when working with steel material, or factor of safety when working with wood material?
Wood.
Why? Why is that?
It's weaker material.
It's weaker? Okay.
It's susceptible to more damage, or it
More
just
breathing,
breaks
more breathing,
automatically.
you
It
have
doesn't
different
have enough.
Different variations. It's very difficult to get consistent quality of wood. It depends on the tree. But in the mill, in the steel fabrication and like hot rolled steel, it's a heavy industrial endeavor, and you can have like quality assurance and quality control. And that's exactly why gamma M is 1 in steel, because we're so confident that we can consistently produce steel with yield that is 275 MPa. We don't need to reduce that much. With wood, we need to be careful with what we use. Excellent. All right. So what about the stress on the section? How do you calculate the stress on the section? What is the stress equation for a rectangular section? What is the bending stress equation for a rectangular section? So this is a rectangular section.
Force over area.
Well, force over area is for axial load. What is the stress distribution for a bending stress? Bending stress over a cross section.
Moment divided by length.
Moment divided by length. What is that going to do? It has to do something with that.
أو تضربها فيها عشان تعرف تشيل الكلمتين.
Well, if you get the height or effective height of the section, you can translate the moment into a couple that will create at some point here, everything above this is compression, everything below it is tension. That's why the distribution in the linear, not in plastic stage, in linear stage, the distribution looks like this. If the tip of the arrow is going into the section, this is compression. So this is stress, compression. This is stress, in tension. How do you get the maximum stress at the very top? What is the equation for the bending flexure stress on a cross section? It's very easy. If the distance between the neutral axe and the very top fiber is y, which could be the overall height divided by 2. If distance y is between the mid of the cross section and the top fiber is y, the stress equation, the maximum stress due to bending moment M, it's very simple. Any guess before I write it?
شايف المومنت في الواي divided by area.
By I. It's the moment times y divided by the moment of inertia. That's pretty much it. How do you get the moment of inertia of a cross section that has a width A and a depth B?
A times B squared is B cubed over the cross.
Thank you very much. It's A B cubed divided by 12. How much is y?
Half
is
B.
B divided by 2. How much is M?
Moment.
That's the moment on the section. And that's exactly how the code spell it out. The stress due to a moment, M, is the moment divided by the section modulus. So how much is the section modulus based on this little equation that I did here? How much is the section modulus based on this equation?
هيبقى it's multiplied ففي حاجات cancel each other out.
Yes.
So هيبقى AB squared
Does that make sense? If you substitute I, AB cubed divided by 12, and Y divided by 2, what would be the section modulus?
مش
it's
ال
just
A
multiplying لا
مش
divided
No, the Y is in the top.
مش A B تبقى تحت. احنا بنجيب
Yes, we're getting the section modulus W. So from this equation, nope.
So it's gonna be B over 2 divided by AB cubed over 12, right? So one of the B's is taken away, but I don't understand where we got the 6.
Yeah, because the 12 is in the bottom and the 2 is going to be in the top, so you can do the math and it will become 6, all right? So that's what the code says about the section modulus. This is the elastic section modulus. If you have a solid steel member, the elastic solid steel member modulus is the same formula. What's different in steel is the plastic. The plastic stress distribution does not look like that. Can you guess what does the plastic stress distribution look like?
Square.
Yeah, square. Because this point will reach yield and then it cannot take more stress. It will wait for the fiber next to it to reach yield and it will propagate all the way to the center line in both tension and compression. All right? So wood doesn't behave like that. Wood, when it reaches the maximum stress, it will rupture. It will have cracks and it will tell you that it can't take no more. All right? There are a few things that you take into account. First thing is the service class. What is the service class of the structure? It has to do with, are you going to protect your element or your structure member from the elements, or is it going to be exposed? So are you designing an outdoor shed that is going to be exposed to rain, wet, long time, in the snow, in the cold, or is this indoor? Like, do you notice how the indoor wall doesn't get exposed too much to rain or wind or sun, yeah, because it's indoor. So if it's external use, fully exposed, if it's external use, fully exposed, that's called service class 3. And you gradually reduce the exposure of the classes till 1. 1 is intermediate floors or internal partition walls. So internal walls, the difference in temperature is not going to change much. Most of the time we're going to have AC, we're going to have some control of the temperature. It's not going to have very big wide variations because wood is very sensitive to like big changes of temperature. Can you think of an example of how wood is sensitive to change in temperature? Doors is a good example. You can sense it. Like, you know, when one season the door is working fine, another season it kind of gets stuck, it get jammed. All right. So first we need to know the section class because we can figure out the modification factor. This equation, this table is from the code. It's table 3.1 in Eurocode 5.
Wait, is this code booklet? Code booklet فيها concrete tables.
ما حطها
هو big one.
All right. So what is all these numbers?
constant K?
3 things. There are 3 things into play. There is the service class. Is it fully exposed, class 3, or indoor, class 1, or just a cold roof environment, class 2? So that's the first variable. The second variable is what is the material? Is this solid timber? Is it Glulam? Is it LVL? Is this plywood? And so on and so forth. So for each type of wood, it's not types of wood, it's like a product, wood products. If it's an engineered wood like Glulam, you take into account that this is not one natural piece of wood. This is pieces glued together. So obviously the factors might differ. One last thing to take into account. The load duration class. Can you guess what the load duration class is?
Lifetime of applying the load?
Yes, the duration of the load on the structural element matters. Because if you put a heavy load on wood for too long, creep might be needed to take into account. Over time, with the exact same load, it might deform with time. So if it's a permanent load, I need to take some factor into account. If it's an instantaneous load or a temporary load, can you think of example of a temporary load on a wood structure?
Windows.
Windows? Okay. So people, I like that. Why live load is not permanent?
Because it changes.
Because it changes. Because people come and go. So this has a different value. And back to like the window example. Well, it has to do with wind. Because is wind a permanent load or is it like an instantaneous load? It depends. You can get like a constant wind or you can get like a high storm with like gusts of wind that will push against the structure. And this is table 2.1 and table 2.2. It goes into the duration, the load duration classes. There are 5 main classes. Permanent, it's always there. Self-weight, as an example. So table 2.2 gives you examples of these classes. The second class is long-term. Long-term if you have storage.
Furniture, for example.
Furniture, thank you very much. Third one is medium-term. That will be like live load, snow. Short-term, wind. Wind is not going to be applied usually like when it's windy outside, it's temporarily windy. Or a gust of wind. that is a strong gust of wind. It could be like an instantaneous load or accidental load. Something that might bump into your structure is not going to be there forever. All right, there is one more table. This is the material factor of safety. This is gamma M. In steel, you guys are used to taking it as 1. That's a Eurocode thing, by the way. Different standards might use it differently. Might actually put some factor of safety for steel.
So this is for the SLS surface load?
This is for ultimate limit state.
Okay.
This is for ultimate limit state. These are the factors for gamma M. So if you're using solid timber, the factor is 1.3. So when you're dividing by 1.3, are you increasing the strength or are you decreasing the strength? Decreasing it quite a bit. 1.3 is very different from 1.
It's multiplication, so it's less than 1 value.
Yeah.
Eurocode is,
That's right. That's exactly it. So you're actually using 70%, around 70% of the strength of the material. Use pretty much the same thing for these different types of fiber boards. If you're using the LVL, it's 1.2, and this is going to be the Eurocode table that we will refer to for gamma M. All right, that leaves us with the properties of structural timber classes. So there are guidelines to give classes for grades of wood. You can think of this as like the steel grades. Do you know what the steel grades are? Like when you say like an S275 or S355, it defines what grade of steel is. So it gives a name for this category of wood. Same thing with C14, C16. As you go lower, the wood gets denser and stronger, more expensive, and less available. So there is a note here that you actually might find it difficult to get grade like C45 or C40. It's going to be like a very rare product, but the lighter, less strong grades might be readily available. I want to take you through some of the things that you might find. The characteristic strength property. You can think of it as the ultimate strength of wood. It will be like the FY kind of thing. But it's very dangerous to think of yield when you're doing with wood. It's a different material. So don't mix the two concepts. I just want to kind of guide you the significance of these numbers. These numbers are the ultimate capacity, stress that wood can handle for each grade. Does that make sense? So you start with the grade. You start with your grade, and then from this table, you can get the bending strength, the maximum bending that it can take. This actually goes into the equation that we just talked about. You can get tension parallel to grain or perpendicular to grain, these values, or compression parallel to grain or perpendicular to grain. It makes a difference. And you will find that parallel to grain wood is way stronger than perpendicular to grain. So parallel to grain is very strong. Perpendicular, you can crush it very quickly. The second side here is for stiffness, E pretty much, for these grades of wood. And over there is the density to calculate self-weight. And that pretty much concludes what I wanted to talk about today. We will do some more examples in the tutorial. So if you have any questions, you can come talk to me. If not, I will see you in the tutorial. Let's take a few minutes break and then we'll continue. All right, see ya.